Okay guys, this is section 8 of the chapter, and this is where it starts actually getting a little bit interesting. So far we've been looking at information, pulling that together, and then we're going to introduce you to a new type of particle. Strong, weak, and other types. Okay, so what we have is basically forces that exist around us. We have force due to gravitational fields, electrical fields, magnetic fields, etc, etc. And if we actually start looking at them, as Michael Faraday did many years ago, they started pulling together. He realized a lot of the forces are quite similar. So electromagnetism we're all happy with, but we've always thought about them originally as separate ideas: electricity and magnetism. And we now have a thorough explanation of electromagnetic fields, the forces due to either the charge or the movement of charges, which is what the basis of it all is. So if we actually think about the forces around us, then we can simplify them and compare them. When we're talking about pushing a car, for example, it's actually our hand that's being repelled by the charges in the car, so it's actually an electrostatic force that's making that happen. And if we simplify this, we actually break down to very few forces indeed. In fact, 4 of them. Now, I've already recorded this video and happened to have lost it, so this is a rehash of it. So it's already filled in, so it's going to be a short video. So, key ideas. Some particles, as we have examined, hold together or push apart protons, neutrons, electrons, all those other particles. So interactions, things that cause things to happen, are actually done by these forces. Now, to fit in with quantum mechanics, we can't have the idea that, for example, an electron that's shooting in towards another one, if we have that coming in, well, in field theory, classical physics, as they get closer and closer, the force between them gets bigger and they will curve away from each other because they're both negative charges, etc, etc, and the force is always continuously changing. Well, that doesn't fit in with the idea of certain amounts of energy, quanta of energy, discrete amounts of energy. So we need to think of something about this, these effects that we see every day, in a slightly different way. So the way that this works, fitting with quantum, is that something will happen at some moment and cause the electrons to shoot off in opposite directions. And it's a very distinct time that this happens. Could be a bit sooner, could be a bit later, but it doesn't really matter, as long as there's a point at which energy from one of our electrons and momentum, which go together, momentum and energy, gets passed on to the other particle, and the other particle gets knocked out of the way. Bit like someone on roller skates or on ice skates. If they throw something at another ice skater, the fact of them throwing that object out means that they recoil. So there's a change in their momentum, and when the big heavy thing hits the other ice skater, it knocks their momentum. So this idea of swapping momentum and giving forces, producing forces due to rate of change of momentum, or energy, whichever way is easier to think of, happens because of this idea of having to fit in with a certain fixed amount of energy. Now, there is a certain rule that goes with this, and that links into that if you borrow, basically need a certain amount of energy, it limits the time that you can use it for, and this is why you need this sudden instant. Now, what we could do, just to add it up, we could have, we could have a less energy, so it has less of an effect. Maybe you throw a lighter ball at them, and then a second one, and then you recoil. Okay, so each one has a bit less energy, but it means that each one can last for a bit more time. And this rule is that this number has to be less than a fixed constant, which is Planck's constant. So this is a really important concept. This idea is how we explain these things called exchange particles. But actually what we've got here is Heisenberg's uncertainty principle. The idea that we don't actually know where everything is exactly at every moment in time. The universe is a bit fuzzy. So I can see my car out the window. I know it's there, but the electrons in it, I can't tell you exactly where they are at the moment. If I could freeze them at a moment in time, they would look blurred. If I could, for those who know a little bit about camera work, what I could do is look at it in a different way, and I could actually not freeze them in that moment of time, or try to freeze them, but I could blur the time, and then I would see them in the exact position. So either time or their energy, their movement, will be blurred. And we can look at, there's different versions of this where we can think about momentum and position, energy and time, but the kind of link together. There's a fuzziness. Now it's not very fuzzy because this is 6.63 times 10 to the minus 34. So it's a very small amount, this quanta. Okay, but this gives us an idea of being able to play around a little bit with the universe, and this is where exchange particles come in. So how does it link in? That interestingly, it gives us an idea for these exchange particles, in that they're kind of particles, they're kind of not particles. We call them virtual particles. So these virtual particles are the ones responsible for the forces and interactions that make things happen. So why are they virtual? Well, you can't detect them, you can't get in the way of one of these messages being carried across, otherwise the message would not get carried across. Okay, so if you watch programs with Jim Al-Khalili and people like that, they talk about information. Okay, quantum tunneling carries information. They're talking about the momentum and energy being transferred. So these virtual particles are responsible for our four forces. I said four forces. Everything simplifies down to four forces. So what are these four fundamental forces that, when you get further away from them, just look like our everyday push, pull, up thrust, etc., etc. Okay? Now, interestingly, two of the four we don't notice. So actually there's only two in everyday life. Key. Start off, we'll work down. As I say, I've already filmed this, so the answers are already there. Gravitational force, so the force due to gravitational fields, the force attracting masses. That is everywhere, that exists across the universe, and it affects everything with mass. In other words, everything that's a particle. Now we know that, again, everyday life, we know that atoms are held together by their electric charge. Magnetism, as it spins, is creating those magnetic poles that we use in, we looked at when we looked at domains. It affects everything as well. It lasts forever. It will travel, but we know it gets weaker the further you are away from the charge, but it does actually still travel to infinity. Both of these have the same descriptives, Potential in either of these fields is work done moving something from infinity. So these will reach all the way across the universe. It's just the electromagnetic will only work on anything that's charged. Okay, so gravitational is universal in that it works on everything. Electromagnetic, everything that is charged. We've also had a look at the nuclear strong force. And that means anything, obviously, is in the nucleus. Hence the name nuclear strong force, but that's the attracting and repelling, that nuclear strong force graph for all hadrons. Now, I should say the graph is classical physics, again, just like the old way of looking at forces as a curve, okay, building up and going down, whereas this is actually looking at it in terms of a particle exchange. And we have that in our picture as well, but we'll pick up on that in a minute. Now there is one more force That's not really a force, but it is an interaction, okay? And that interaction is what causes things to change, rather than causes things to move or be attracted, repelled, etc., held in position. There is another force that affects things only in the nucleus. So it is a nuclear force, and it is a weak force. So we have a nuclear strong force, we have a nuclear weak force. It doesn't mean it's weak. What it means is it's very improbable. So if this happened all the time, if the nuclear weak force was stronger, for example, then the decay of particles in the sun, causing nuclear fusion, and that exchange of what goes on, which we'll pick up again in more detail, that changes would mean the sun would have burnt out millions of years ago. Okay, so if the nuclear weak force was stronger, okay, was stronger there, so more probable, then things would decay faster. More particles would decay every second. The sun wouldn't last as long. There's a fair chance we wouldn't have intelligent life on Earth. Life wouldn't have had enough time to develop if the sun didn't last long enough. So very profound, but almost unnoticeable in everyday life. Okay, so those are our four forces, or perhaps more correctly, the four interactions, but they are called the four fundamental forces, so bear with us. And the interesting thing about them is how they compare to each other. So those are the rules on how they work, but some are much stronger than others. So the nuclear strong force is, as we've already seen from the graph, way stronger than the electromagnetic force. Okay, so if we do calculations based around this, then we'll find that around about 100 times stronger than the Coulomb force is the nuclear strong force, which is good because it holds the protons together in the nucleus. Otherwise, if it was the other way around, nuclei wouldn't exist. They would push apart. Very short range though, so nothing outside the nucleus will be affected by the nuclear strong force. Okay, it actually has to be within the nucleus for that to actually take effect. So although it's really strong, it doesn't go very far, whereas electromagnetic force will affect across the universe. Now, in reality, of course, we don't notice that a great deal, because when you have enough charged particles, they tend to form atoms, and atoms are generally neutral. So as things get bigger, if you were thinking about you, you're generally not charged up. Your charge moves around and makes your nerves work and things like that, but you're not electrically charged generally as a person, because all of the numbers of protons and electrons basically cancel out, or the charge on them. The nuclear weak force is quite a lot weaker. It's about a 10 millionth. Okay, so 10 to the minus 7 times weaker than the strong force. So its interaction is weaker, but interestingly, the scale is even smaller. Okay, and there is a reason for that comes back into the equation hidden over here. So the nuclear weak force is around about a millionth of a meter, which is about the distance across one nucleon. Okay, so this can exist inside a proton or a neutron or other hadrons, whereas this will actually reach across the nucleus. So particles within the nucleus, doesn't matter too much, but it's still weaker than the strong force. Which only leaves gravity. So how big is gravity? Well, actually gravity is pathetic. It holds the universe together, and yet it is so low in its strength compared to the other forces. And you can do a simple bit of mathematics about this. You can work it out. All of these forces, so that one for example affects everything in the atom. The electromagnetic force, that also affects everything in the atom. So let's just have a quick look at that, apart from neutrons I should say. If we do the basic mathematics of it, there's our strength of our gravitational force. If you do the electric force, then again 1 over 4 pi epsilon naught, obviously because it is a vacuum, as we know it's mainly empty space, QQ over r squared. So if we take the radius of an orbit of an electron, or, because they're the same, we can cancel it out, it doesn't matter too much. We can compare the size of the two, and if you put the mass of a proton attracting the mass of an electron, charge of a proton, charge of an electron, quantifying numbers, so multiplying numbers, so your constants there. If you put the maths in, you'll get a similar figure to that. Okay, the difference between them are around about a million times bigger. Okay, the electromagnetic force is bigger. So gravity is incredibly small. It's so small that basically we're going to ignore it at this level. At subatomic level, it's almost immeasurable. Okay, so particles are not affected by gravity when you're talking about individual particles shooting through space. Okay, so let's move on. In the next section, let's click it over, giving you quite a lot of information. So this idea of exchange particles, okay, that Yukawa put forward and then was built up a bit more. Yukawa then went to work with Richard Feynman, who brought some of the ideas together. And then, as I said, it needed to come into the idea of quantum physics. So I've given a little analogy of people on ice skates. Obviously particles don't all repel, some attract, so maybe a heavy boomerang which swings around and then knocks them towards each other. Yeah, okay, it's a model. But what that means is that if we need to make things move across, if we need that energy and momentum to move across, then they have to be different because of what they affect. So different particles will produce these effects. Each of these four forces need something that will carry the energy across to the other particles. Okay, I'll just put that in. So what do they do? Well, some of them we need to know, some we don't. So the interaction, okay, the strong force, again keeping with the same order, so the strongest force has particles that hold them together within the quark system. So within a proton we tend to call them gluons. You can get that as an answer, that's fine, but normally the particle that matters is the pion. Okay, so the pions are what keeps protons and neutrons together in the nucleus. It's about scale, basically. Pi plus, pi zero, pi minus, different types. As I said, it acts on all hadrons. So these keep the nucleus together, but if you smash particles together, then that are made of quarks, and rearrange the quarks, it involves the pions as well. So again, the energy moving between them, the energy carried and transferred, is all due to the pions being exchanged. Now I've greyed out gluons, but again, you can get the mark for using gluons. Slightly more humorous as well. Electromagnetic, well, we've seen that. We've seen that it's photons that do that. Photons will create a pair of charged particles, or charged particles, as they annihilate, will create photons. We know that photons since 1905, well actually known before, but Einstein in 1905 explained why this idea of photons being the thing that gave energy to electrons to jump them out. So photoelectric effect depended on photons releasing charged particles or changing the charge within atoms so the particles can escape. So photons are the way of describing that. Weak force, I'm a bit of a quandary here because they have something called the W particles, which makes sense. So you've got W plus, W minus, and then Z. So I don't know why Z came from. But yeah, there is a version. Again, we're not going to experience that because it's a bit more of an obscure in terms of where you'll find it. But I don't know why they didn't call it W0. But again, all things that decay are hadrons. It's the quarks that decay. So hadrons will decay, as will mesons. Okay, but for us, basically, it's the hadrons. And then the last one is a bit interesting. For gravity to be explained using quantum mechanics, gravitational fields have been really well explained using relativity, quantum mechanics, we know really well, explains everything we see around us. Okay, both of those, I have not got any evidence to disprove them, but they don't quite fit together. If they do, then we will need particles, which have been called gravitons, that will shoot between masses in a twinkling of an eye, even across the width of the universe, because gravity is across the width of the universe. So, yeah, they will have to be so fast, therefore they will have to be so light, so small mass, they'll be almost unmeasurable. To go back to the idea of classic physics, you know, gravitational fields, rather than talking about gravitational particles, you know, we've only just found evidence for the Higgs field and explaining that, and we've only just measured, you know, we have the Higgs boson, which is the particle that works on this. We haven't got, I should say, Higgs field in here, but yeah, we have this idea of that for what things give things mass, but gravitons will be harder to find. We've only just managed to measure gravitational waves, ripples in the gravitational field. So it's going to be a long time before we get to gravitons. Anyway, so a little bit of the maths of it. There's our maths that we're putting in. So it has to be, the energy and the time has to be less than allowed by Planck's constant. That's how they can borrow energy. Okay, so they literally within the universe borrow enough to create something that lasts for a very short time. You can also, again, fitting in with theories, especially nearer black holes where we have noticed them, but pairs of particles can borrow energy from the universe as long as they last for a short time. So often a lot of the theories actually fit together and agree on this, and that, you know, point in space you can get an electron and a positive electron and a negative electron being created, but they have to come back together. Well, they're plus or minus, so they will. They don't have enough energy to escape from each other, and those then recombine. Okay, and it's that means they've only lasted for a very short amount of time, which allows enough energy to create the two particles. Now, if they're near a black hole, and this is happening near the event horizon, so where basically the point of no escape, if one particle shoots in, then the other one, again by conservation of momentum, is in the opposite direction. It shoots away from the black hole, and this is the idea of Hawking radiation from Stephen Hawking's theory. Streams of particles have been seen coming out from black holes. We can detect radiation from black holes. It's not from inside the black hole, even though it's a mass, but it's actually just at that edge, event horizon, at the edge where it falls in. So some of the particles fall in, half of them don't. So we've got a lot of evidence for it elsewhere as well, happening all the time in space. So you don't need a particle accelerator. Okay, so a little bit going on here, and just to add a bit more to this picture, why do these not travel very far for the nuclear strong force and the nuclear weak force? Well, if you go back to the PowerPoint with our cuddly particle zoo, as the toys are called, you'll find that pions are quite massive, and W's and Z's, the weak nuclear particles that carry the weak nuclear force, are really massive. And because you need a lot of energy to create a lot of mass, they last for a very short time, so they don't travel very far before they decay. Okay, and that's how it all works. And it's a bit like this idea, as I said, an analogy there of lending money. If you borrow a little bit of money, people aren't too worried. They'll give you days to pay it back, or maybe even forget if you borrow 10p for the bus. But if you borrow £500, they're going to want it back in a really short time. Yeah, so it's kind of common sense, really. Now, we're going to go on to diagrams in the final chapter, but I'll give it here because I haven't explained it. Particles change at a moment, and this is the exchange particle. So as something changes, as this exchange particle is emitted, it changes what's happening with the particle here. So say we've got a proton, it may decay into a neutron, or maybe it just changes direction, whatever. Okay, depending on what the force is. Let me just move it in. So if it's just it changes direction because a bit falls off, that's a strong force, not being quite strong enough. But if it's decaying, then this would be a W. Okay, whichever it is, it doesn't matter. If it's changing charge, for example, I should say, then it will be the photon. So again, it depends on what's happening to the particle. It's caused by this. But delta T, delta E, energy needed, it'll only get so far before it decays. It has to pay back its energy. So that energy is released by creating particles. Okay, 2 or 3. It's a bit more complex than pair creation because these aren't photons. Okay, but most, if you look at all the ones that we're going to with photons, it's always 2. Okay, 2 partner particles. So that's the idea. That is how far its range is, and the range is of course dependent on its velocity and the time. So if time is really small, the displacement it travels is really small. 10 to the minus 18 meters. There we go. So last bit is again way beyond the course, but I know you've all heard about it and the discovery of it, etc. And there's enough jokes on the internet. The idea of the Higgs field, okay, or the Higgs boson. The Higgs boson being an exchange particle. These are all bosons. Bosons being exchange particles. You don't need to know that, okay, but you can memorise it because you're bound to, because you don't need to know it. What that means is there is a process to explain a lot of stuff. Everything is quantized. Everything has a definite value. We don't know why. Will we ever know why? We don't know. Except for one thing, and that's mass energy. So something has created a whole range of masses, and that theory was dreamt up by 3 guys, okay, from across Europe. It was at wasn't Glasgow University, but one of I think it's Strathclyde University, I think, where Peter Higgs worked, and he came up with the main idea, hence it's named after him. And when they discovered it, in the live clip that I clicked on, I put the web link to on the second PowerPoint for the chapter. That takes you to news about that being live. So he was there when it watched. It's not often many particles that have been predicted are watched by the discoverers because it takes a long time to build the machines. They tend to die off, the scientists, unfortunately. So we could make a joke, but we won't. The idea with the Higgs field is basically when things travel through a Higgs field, they're affected by the boson. There's this additional force interaction, and what happens is different particles are affected differently by it. So some particles, photons, are really not affected by it at all, so they don't gain mass. Okay, it's a bit like kind of running through treacle. Certain things, if you try running through treacle or mud or whatever, some people really seem to stick mud. So people in the woolly jumpers, as they fall over and whatever, they're going to get a lot of mud stuck to them. Those in a nice nylon outer coats, it tends to slide off and it doesn't affect them much. So there's a way of explaining why different particles have different masses. The basic idea is this. Now I'll share with you the video, share with you the PowerPoint. There's a newspaper, I think it's New York Times, gave a lovely animation, and it's a really nice idea about it. It's a bit like running through snow. But yeah, this is all your idea is, okay? It's all about how much it slows down particles, and using the idea of momentum. If you're slow, it means you've got a big mass. So it's all about this idea of mass, inertia being difficulty to move. Okay? And that is section 8. When we go into section 9, we'll explain what the forces are doing, a bit more. I've actually done loads of it today. What's going on with all these different forces, how they fit together, and as I've just shown you with a bit of a picture, how these Feynman diagrams, as I say, the guy who worked with Yukawa, how the Feynman diagrams show, I think in a really visual way, what's going on.